Good morning. We can see another vibration analysis. In this case, we can study a massed suspended foreign spring system as the schema in see in this figure 1, where there is the system of spring K1 suspended in two parallel spring K2 for K3 and after a mass M. In this problem, it's important to understand the flat shape of a system in different situations. So we can see three different position: initial position, allowed, where the spring K1, K2, K3 is not stressed for the mass M. So the mass M is not agent. So this is unstretched position. In the situation B, we can the mass is free to agent, so there is a static equilibrium where the mass M have in static movement. So the x static movement is equal of x1, where x1 is the elongation of spring K1, più xp, where xp is the elongation of spring K2 and K3 arranged in parallel. So the equilibrium equation we can write with weight is equal of mass for the gravity multiplied for kappa, the stiffness equivalent for the x static, so is the moment in the static situation. Where kappa equivalent is the equivalent vertical stiffness of the spring system. Now we want to calculate this value kappa equivalent. The spring equivalent, the spring in parallel, K2 and K3, we can write the equivalent stiffness, kappa parallel, equal of simplify in simple way the sum of K2 for K3. For the spring in serial, the reciprocal of total equivalent stiffness kappa equivalent is the sum of reciprocal of the individual stiffness. So we can write 1 divided kappa equivalent is equal to 1 kappa 1 plus 1 kappa p parallel. So substitute kappa p in we can find this equation. We can rewrite this equation in this way, find a common denominator. Inverted the equation, we can solve kappa equivalent, where kappa equivalent is equal to kappa 1 multiplied for the kappa 2 for kappa 3 divided of sum of the three stiffness. The natural circular frequency omega is given of this formula, so we can rewrite this formula in this case in this way, and so finally omega n is equal to racine for kappa 1 multiply kappa 2 for kappa 3 divide of m of sum of stiffness of three kappa 1 plus kappa 2 for kappa 3. The natural frequency is divided for 2p, so we can write finally this formula. The equation of dynamic equilibrium is equal add m for second derivative of x time is equal of weight when kappa equivalent for z, where z is the sum of x static plus x. So zx static plus x, and we can write using the formula 2. Formula 2, we can rewrite in the, and then finally the equation of dynamic movement is equal to m for the derivative of x2, derivative second derivative in t of x, plus kappa equivalent for the movement x should be 0. Okay, so is the equation, and we can simulate this equation, this harmonic movement, with in Python code. we can see here. We can explain what to do this code, and okay, there is the import of some library in the top, in the line with 8, 9, and 10. Import mat is import the mat module to perform basic mat operation, example square root. And after import NumPy, send library to arranging of array of. So and after import Matplotlib is the module to plot the graph. After we can define a function where is calculate the displacement, and in this the input of this function is m la mass, kappa1, kappa2, kappa3 is the stiffness of spring, the initial pull x0, and the time duration for plot the G is equal acceleration of gravity, and after we calculate kappa parallel, we can see kappa2 plus kappa3, and kappa equivalent is equal at this formula. We can calculate before. Omega n is racine of kappa equivalent for m, and static deflection is mg for kappa equivalent. And in this line 35 define the time of duration time. Here is the equation of movement, is an harmonic where xt is equal to x0 plus multiply for coseno di omega n, so the frequency, the 40. Here you can print the result, and after we can plot the graph of the displacement. In this example, we can use this value for the mass is equal to this kilogram, and after kappa 1 500 Newton for meter, kappa 2 200 Newton for meter, kappa 3 is 200 Newton for meter. Initial stretch is equal when 1.5 in meter. A simulation time is 5 seconds. And after we can call the function calculate displacement we can see before. The solution, the output of this program is this graph, okay, with harmonic function. So we can apply 1.5 displacement to start, and after there is coseno formula graph of this displacement. Is an harmonic value. We can also make a simulation of this displacement, where we can see the movement of system of spring with displacement in the zero static value. So this is value of static. Here is the input of the system parameter of this value, and after can see the vertical displacement in the time how can movement. Okay, we can change clear K1 and K2 and calculate the different frequency for of form. Okay, it's all. Bye.